I'm Dave Baring, Technical Director here at TriStar, and welcome to another Tech Talk. Today it's another one of the quadrant products that we're going to be talking about, and specifically we're going to be talking about Fluorosint. Now, Fluorosint is a fairly unique material. It is Quadrant's family of PTFE products, and they're fairly unique in the world of PTFE compounds. And so as we review this particular family, keep in mind some of the very unique features as you consider in the future designs where PTFE might be the right call for you. Now, Fluorosint, if you look at our infamous triangle again, the Fluorosint falls into the high performance materials, and it's up in the peak PPS range. Fluorosint, being a PTFE based material, is going to have a continuous operating temperature of actually higher than 550 degrees. 550 is a good top end number. 500 is a more common number for continuous operating temperatures, but 500 to 550 is a pretty typical design number for the Fluorosints. Now, the Fluorosint family is really made up of three different materials. What makes Fluorosint unique is that the proprietary filler that's used offer a PTFE product with extraordinarily low thermal expansion. That is one of the bugaboos of filled PTFE, is that the thermal expansion rates are really all over the board. And you can have rates running from 4 to 12 on different types of filled PTFEs. And the other thing you have to be concerned about is that the direction of the material has a lot to do with its thermal expansion rate as well. You know, the cross direction versus the molded direction. So having a material that starts off with an extremely low thermal expansion rate in either condition is a big plus when you're looking for the other features that you want to get from a filled PTFE. The other unique thing about Fluorosint is it has very low deformation under load, especially compared to other PTFEs. And if you know anything at all about filled PTFE, is that you will get as broad a variety of deformation resistance as you do thermal expansion properties. Some materials do very well under load. Other filled PTFEs don't do well at all. They cold flow very, very quickly and with very little load on them. So the Fluorosint family is, those are the two key factors, I would say, in terms of why they're so much better over other filled PTFEs. Thermal expansion properties and low deformation under load. Now, the three grades that we're going to be talking about, Fluorosint 207 is the FDA compliant material. It's an excellent bearing material. It's fully inert to chemicals, as are all the Fluorosints. Obviously, being an FDA compliant material, one of the areas of design would be in the food processing world, where it could be exposed to high pressure steam clean downs. The sodium hydroxide solutions don't affect it whatsoever. So it's a very stable material for both cold applications, hot applications, high loads, low friction, where there are in fact direct food contact. And the same holds true for pharmaceutical. If you have applications where there could possibly be some direct food contact or pharmaceutical contact, the 207 would be the correct call for that environment. Fluorosint 500, the unique part of the 500 material is that it has 9 times greater resistance to deformation over a regular PTFE. So in terms of its ability to take and maintain structural integrity under load as a PTFE, there is none better than the Fluorosint 500. The other unique thing about the 500 is that the thermal expansion rate is very close to aluminum. So from the standpoint of design, it's very easy for us to design and hold tight tolerances over a very broad temperature range, and especially if we're trying to match this part up with other metals. And then finally, the Fluorosint HPV, which is the newest version of Fluorosint. HPV stands for obviously high PV. PV, if you recall from some of our earlier videos, PV is pressure times velocity, which is a measurement device or measuring device that we use to determine the capacity of a material to withstand loads and speeds. And so in this case, the Fluorosint HPV has been designed to specifically work as a bearing material and also as a seal material, we have found, with higher PV ratings than other filled PTFEs. In fact, the HPV is double the normal ratings of other filled PTFEs. So we'll talk more about that as we move forward. Now, some of the main characteristics of the Fluorosint family: very high operating surface temperatures. As I mentioned before, 550 is not uncommon for filled PTFEs, and that would include all three of the fluorosints. Load-bearing capability, not normally attainable with conventional reinforced PTFEs. Again, because of its extraordinary resistance to deformation under load, the fluorosints can work very well in some much more extreme conditions that you may not use other filled Teflons in. So it's a nice option to have if you need all of the other features of a filled PTFE. But the one downside is the fact that it's unable to withstand those high loads. Good dimensional stability. Again, because of the thermal properties of the material, it's very, very stable in terms of design. So we can hold tighter tolerances and make a much more functional part. Excellent chemical and hydrolysis resistance. The material is unaffected by steam and water, zero absorption, and chemical range, the full pH scale. So it's a very inert material. Outstanding UV and weather resistance. As with most filled PTFEs, this material can withstand UV, gamma radiation, all kinds of things to a certain point. But certainly UV and weather resistance. So if you have to use it in an outdoor condition, you can rest assured that it's going to hold up very well in those conditions. Good electrical insulating properties. The filler inherently improves the dielectric values of the material. So it's something that you can use as a dielectric standoff or just simply an insulator device in electronics. Good wear resistance, low coefficient of friction. The K factor of this material is very low, ranks right down there with some of the higher end filled PTFEs in terms of its life expectancy. The coefficient of friction is fairly typical of filled Teflons. And again, if you've heard any of our other presentations, you understand that coefficient of friction is relative to a lot of other factors. But as a rule, the fluorosints are on the lower end of the filled PTFE in terms of friction values. Low flammability, it self-extinguishes, and then it is suitable, the Fluorosint 207 is suitable for direct food contact. It does have the FDA clearance. Now let's take a look at some applications. First of all, the gas chromatography application for Fluorosint 500. This is a material that was selected for this chromatography device, and specifically it's being used in its valve. It has to dose a certain amount of flow in order to get the analysis that they require for a media that's being tested. They had used other rotors in the past made out of different types of filled PTFEs, and even had tried the Peak HPV. But the Fluorosint 500, because of its thermal stability, because of its strength, inherent strength, it worked much better in terms of its compressive properties, in terms of its thermal expansion, And it also is a ductile enough material that it could in fact perform sealing function as required. So Fluorosint 500 in this case was selected for its temperature resistance and its dimensional stability, low coefficient of friction because there were some dynamics involved, good wear resistance, and friendly towards the mating surface. This was a situation where it was running against stainless steel. And then in terms of its sealability, it had good elasticity, and even though it's got that high deformation resistance, it still is compliant enough to where it can be used as a sealing material in a variety of different conditions. The next one we'll take a look. The next thing we're going to take a look at is the thermal expansion. You can see here the coefficient of linear thermal expansion for this material is very low when you compare it to other filled PTFEs, and you'll have to take my my word on that because this doesn't really show a comparison, but Fluorosint 500 does have a very, very low thermal expansion rate as compared to other PTFE based materials. And that's, again, one of the big selling points of the Fluorosint 500. Another application for Fluorosint on the 207 material, in food packaging, not so much here in the U.S. In the past, but it's beginning to show up more and more in our packaging. And having just attended the packaging show, I can tell you that it's probably going to be more predominant in the very near future. But a lot of the food packaging that's done around the world is finished off with a particular type of film, and that's especially true in liquid packaging. So milk cartons, juice cartons, things like that will have a film that is heat sealed to the packaging to just ensure that it maintains its reliability and that there's a good positive seal of that film. And in this particular case, the customer used to use virgin Teflon. Obviously they were looking for its temperature resistance, and in this case the sealing heads were operating at 375 degrees. Because of the type of films that are being used in this application, they wanted to be sure that they got good release properties, and of course PTFE has very good release properties. But in the case of this particular machine, the life of these pressure plates was fairly short because of the abrasion. Because of the dynamics of the application, the packaging paper tended to be fairly abrasive to the PTFE and would wear it out rather quickly. So the resolution to that problem was by switching to the Fluorosint 207. They dramatically improved its resistance to abrasion simply because of the type of filler, and again that deformation factor comes into being. So the 207 was a good positive fix. It dramatically improved their life expectancy on these particular pressure plates. And looking at the values there, high temperature resistance, good thermal insulating properties. It's physiologically inert. So in this particular case, even though it wasn't direct contact with the food product itself, it did meet compliancy on the machinery. Low coefficient of friction, which is part of that release mechanism that they required. The good wear and abrasion resistance just from the normal dynamics of the application. And then anti-adhesive properties, which would be part of that anti-stick low friction property. Now, an application for the Fluorosint HPV. At TriStar, we do a lot of work with special seals, and this runs the gamut of type 2 hydraulic seals to high pressure spring energized PTFE seals. And we have, over the years, used a lot of different materials for these spring energized seal devices, but when the Fluorosint HPV came on the scene, it seemed like a natural because of its PV ratings being double that of some of the traditional materials that we have used. And so we put it to the test very quickly, And in some applications for gas compressors where we had pressures up to 5,000 psi and cycle speeds of 450 feet per minute. Now, if you take those numbers and understand PVs, if you were to combine those two numbers to come up with the PV, you would scratch your head and say, no way, Jose, it's just not going to work. The unique thing about certain types of seal designs, the geometry kind of changes the rules. And in this case, we were able to change the rules fairly dramatically by going to the HPV material. We were able to go to some extraordinary PV ratings on these seals and get the lifetime that we needed to be successful for this particular device. Now, the design of the seal is obviously critical, but some of the problems that you have with high pressure, high speed sealing materials is dimensional stability. You get thermal expansion rates that cause the PTFE jacket to expand rapidly. That increases friction, increases wear, and it just starts this whole ball rolling to a failure. By starting off with a material that was already much more dimensionally stable, without giving up the friction values, without giving up the wear values, we just found we had a very nice combination here of a material and a geometry to successfully solve a very difficult situation for one of our customers. So, again, looking at the bottom line reasoning, high temperature resistance, good thermal stability, i.e. dimensional stability, extremely high PV ratings in these types of applications, good low coefficient of friction, and then the good wear and abrasion resistance. A couple of features here that we just want to review quickly. Again, the fluorosints all have pretty much the same values. High temperature resistance is obviously a big part of that. And I should mention too, low temperature. These materials are also good, just like any filled PTFEs. These products are also good down to very low temperatures, down into cryogenics in some cases. The fluorosint, especially the HPV grade, with its double PV rating over traditional filled PTFEs, is a huge deal when we're looking at bearings and seals. The low coefficient of friction, and again, as I mentioned in other presentations, friction is a number to start with. There are so many other things that you have to take a look at, and we especially find that in seal design, where the geometry of the seal is just as critical to the coefficient of friction as the material itself. So coefficient of friction, yes, it's a low number compared to other thermoplastics, but it is also very relative to the application. A good wear and abrasion resistance. And I mentioned the abrasion resistance again because most filled PTFEs don't do well in abrasive environments. The fluorosints do very well relative to other filled PTFEs when it comes to abrasion. Good thermal stability. We can't mention that enough. That's probably one of the biggest selling points of the whole fluorosint family. Thermal stability, dimensional stability, from the standpoint of design is just very, very critical. And then finally, the deformation resistance under load. And that, again, looking at it from a steel standpoint, that deformation resistance translates to much better life if you've got a material that's going to be stable under pressure, under load. It just goes a long, long way. A couple of charts here just to give you some ideas comparing the fluorosints to other filled materials. You can see the fluorosint 500 in the figure on the left here. The deformation under load is about 1%, and this is at 2000 psi at 122 degrees Fahrenheit. Obviously, deformation under load is also relative to temperature. So these numbers are, basically the numbers that are used for design and for comparison. But you can see 1% is extremely low compared to even the glass-filled PTFE, which is up over 8% deformation. So on the right-hand side, coefficients of linear thermal expansion, you can see again, compared to aluminum, compared to glass-filled Teflon, and then just virgin PTFE. Very, very stable with the two fluorescent materials there. And so something that's of great value from the standpoint of design. Now the fluorescent is available in extruded rod. It's also available in sheet and also in molded stock, molded tube stock. So if you have an application where you think the fluorescent might be a good candidate, especially if you have a bearing or seal application, we would invite you to contact us regarding the HPV material. We've had just very, very good success with that. If you're really pushing the extremes, and again, if you need the different values that you get with a filled PTFE, you know, the good thermal properties, you know, the high and low temperature ratings, the low friction, the self-lubricating properties, dielectric properties, chemical resistance. If these are key factors that you're looking for, but the products that are out there right now just don't quite do it for you, consider looking at the fluorescent, especially the HPV material if it's a, like I said, a bearing or a seal application. If you have any other questions about fluorescents or any of the other quadrant materials, we invite you to contact TriStar either by calling us or by contacting us through the website. If you have a particular bearing application, you can use our bearing design worksheet on the website. You can also use that for seals. If you have an application where you've got a high pressure seal or you've got a design right now that's just not cutting it, you may be using a spring energized seal now that's just not quite cutting it. Give us a call and let us see if we can help you out with one of these fluorescent materials. And we have a couple of seal engineers on staff, and we can certainly be of value to you as a partner in design. So thanks again for joining us. We appreciate the fact that you are interested enough to go online and check this out. Visit our site as often as you want. Feel free to contact us through our blog site or through our Ask the Experts. We're available to be at your service at any time, and we appreciate the opportunity. Thanks for joining us, and we look forward to seeing you in another Tech Talk.